Let's look at question B. The speed of the parcel when it slides back to the starting point. Okay, so previously at question A, the block or the parcel is actually sliding up the inclined plane until it reaches stop, right? So what happens in B is they're asking about the continuation of that event. So the parcel initially launched at 3 meters per second, move up the inclined plane, which stop. Then after that, you slide back downwards, similar to something that you throw up the air. You throw up the air, the object slows down, reaches maximum height, then you fall back down while spinning upright. So for this case, you have an inclined plane. Your object slides up while slowing down, reach a maximum height. Then after that, you slides back down while spinning up. Okay, so now they're asking for the second part of the motion, which is the part where it stops, and after that, you slides back down with an increasing speed. Okay, so let's try to sketch a situation to represent, sketch a diagram to represent the situation by language. Okay, so again, this is 35 degree, but right now the block is, or the parcel is actually at the top of the inclined plane, and it was initially at rest, but now it is going to slide back down. Okay, it is going to slide back down, and they ask, when you reach the starting point, which is somewhere over here, what will be the velocity or the speed of the parcel when it slides back to the starting point? Okay, so let's sketch a free body diagram. Once again, I believe the free body diagram will be different for this case because now your motion is in a different direction, so kinetic friction will probably be in another direction right now. Okay, so again, you have our x-axis, you have our y-axis. Okay, 5 question. First question, does it have mass? Yes, it has mass, so there will still be weight. Next question, connected to any strings, ropes, or cable? No, not connected to those, so you don't have tension. Next, any force being explicitly mentioned in the question or in the diagram? Well, the question didn't say you push the block and you push the parcel down the slope. No, they didn't say that. And the diagram also didn't explicitly say that because it's a diagram that I draw. The question didn't say anything, so I don't draw anything extra. Okay. Next, is there any contact surface? Yes, there is a contact surface, so there will be normal force perpendicular this direction. So push, the surface is pushing the block, so it's in the up direction. So this should be the direction of normal. Then lastly, the object, because it is sliding down the slope, and we know from previous from the situation explanation that it's a rough surface, so there will be a kinetic friction in this free body diagram. So kinetic friction is opposite the direction of sliding. The sliding is down the slope, so our friction, kinetic friction, will be up the slope. Okay, then if you label in your angle, which is 35 degree over here, you have your complete free body diagram for this parcel over here. Right now, we are going to solve the problem, and because it's related to speed, and we are going to use back the same idea. We are going to find the total work done, then from the total work done, we find the final speed. Because we know that speed is related to kinetic energy, and kinetic energy can be related to work done through work energy theorem, in which total work done is equal to the change in kinetic energy. So we're going to follow through the same sequence as question A. So what we do in our before we do any net force thing, let's try to resolve the diagram first. The free body diagram, the weight needs to be resolved. So your weight here will have its y component, and it will have its x component. So 35 is near to the y component, so y will be cos. Okay, cosine w, cosine 35 degree. Whereas for the x component, because it's far away from the angle, it will be sine. So this will be w sine 35. Okay, right now I believe you can see the distinct difference between the situation A and situation B. Situation A, both the forces in the x-axis are pointing down the slope. But right now you can see that the forces in the x-axis are actually opposed to each other. Okay, so it's a different situation right now. So let's follow through the steps that we mentioned earlier. in question A, step 1 will be us finding sum of fx and sum of fy. Okay, again, we know that because for y is not going up into the sky, it's not entering the inclined plane, we know that sum of fy is equal to 0. So let's write out the obvious stuff first. Sum of fy is equal to 0. Okay, you can continue to solve it. I believe it's fine to do that. You can say that n minus weight cos 35 is equal to 0. That's why n again is still equals to mg cos 35. This one has not changed since situation A, but the sum of fx is what has changed actually. Okay, we know that when the block is sliding down the slope, initially it is 0 meter per second. So no matter what, for you to move down the slope, you have to be speeding up. Okay, you have to be speeding up. You cannot be slowing down, because what's slower than at rest? You cannot be slower than at rest. So it has to be a speed up sequence. So this is speeding up. So if you know speeding up is this direction, you know that the motion is in this direction, you want to be speeding up, so your acceleration need to be in the same direction as motion in order to speed up. The velocity and the acceleration in the same direction, then the object will speed up. So you know that the direction of acceleration is in this direction. So because you know that acceleration is down the slope, for your sum of fx, you take the forces down the slope, which is w sine 35, to be positive, because it follows the direction of acceleration. Whereas the force that is opposing the direction of acceleration, which is kinetic friction, we consider as negative because it's opposing the direction of acceleration. Now we know this, we expand weight to become mg sine 35. We expand the kinetic friction to be mu kn, and we can continue to substitute the n here to be replaced by mg cos 35. So this one will be mu k mg cos 35. Once again, we can factorize out the mg because they are common unknown. Now you have sine 35 minus mu k, we can substitute 0.30 cos 35. So this will be the new expression for sum of fx. So now we have sum of fy, we have sum of fx. What we do right now is just to find the magnitude and direction. It's all the same, similar to situation A. So right now you can find magnitude, you can find direction of sum of f. Okay, sum of f, to find the magnitude, we know that it's the Pythagoras theorem combination of sum of fx square and sum of fy square. And because we know that sum of fy is equal to 0, so if you sub in 0 here, this term here will cancel to become 0. So you have a square and a square root left. So what you need to do is just cancel each other out. Then you are left with sum of fx. Essentially, it's just sum of fx left. So it's mg sine 35 minus 0.30 cos 35. Okay, I will not be writing the square and the square root anymore because I know that the y cancel out, then the square root and the square will cancel out. So sum of f will be the same thing as sum of fx without the sign. Okay, the sign is positive already, so there's nothing to worry about. Next, we can find the work done by the net force. Okay, again, the net force will be pointing along the direction of acceleration because the net force will be in the same direction of acceleration. So if the acceleration is down the slope, the net force must be down the slope as well. Okay, so let's write down direction. Again, will be down the slope because you want to speed up. You want to speed up down the slope, so the direction should be down the slope. Okay, so your net force is down the slope, and your motion is also down the slope. So if you combine them together, you can combine the tails together. The net force will be pointing here. Your displacement will be pointing here as well. So the angle will be 0 degree. Okay. So step 3, you want to find work total, or you want to find work done by the net force. So work total, which is the work done by net force, should be equals to sum of the net force, sum of the force dot S. And we can open this up to become sum of F multiplied by S cos theta. Okay, so now sum of F and S, they are both in the same direction, so this should be 0 degree over here. But let's sub in the magnitude of sum of F. Magnitude of sum of F, again, it's mg sine 35 minus 0.30 cos 35. That's what we did in step 2 just now. S, the distance traveled, well, they say when you want to slide back to the starting point, right? So if you are sliding back, if you are sliding back to the starting point, it has to travel the same distance as situation A. So if situation A travels up by 0.560 meter, for you to slide back to the starting point, you have to travel the same amount, which is 0.560 down the slope, in order to obtain S. 0.560, the same amount of distance traveled up the slope and down the slope. So now you are left with cos theta, and you know that cos theta is 0 degree, so it will be 1. So if you put in everything, I believe you get mg sine 35 minus 0.30 cos 35, and you have your 0.560 at the back. Cos theta and cos 0 will be equals to 1. Okay, now you have your work total already. You are going to use work energy theorem to relate the work total with the change of kinetic energy. So let's write in the middle, work total is equals to change of kinetic energy. It has to be work total, not any kind of work total. So again, you can open this up, half m v square minus u square. For this, okay, let's write down mg sine 35 degree minus 0.30 cos 35 degree 0.560. Okay, the m here we need to be crossed out, so we can do substitution. We are looking for the final speed when you reach the starting point. We know that initially it is at rest. Okay, so 9.81 multiplied by sine 35 minus 0.30 cos 35 0.560. Okay, so all the substitution are done, and you know that initially it was at rest, and sliding down you want the final speed. So there's only one unknown left. You can find v, and if you key in into your calculator, you'll get the final speed to become 1.90 meter per second. And that is the speed of the parcel when it slides back to the initial point where we start. Okay, and the distance that it travels is 0.560, which is the answer for situation A. Okay, so use 0.560 in question B to find the work total. Then from there, you are able to find the final speed to be 1.90 meter per second. And that's how we use work energy theorem to solve this problem over here. Thank you very much.